Hello, this is Andrew McCadden, and thank you for watching this presentation. I will be talking about my project doing long-term prediction of common stocks using a genetically trained Bayesian network. This is for EEL 6825 pattern recognition at the University of Florida. I will begin with some background. So when we talk about stock performance, what are we trying to say by that? We're basically trying to talk about whether or not the stock will make you money. But performance does not occur in a vacuum. There are alternatives, and so you have to ask whether or not your stock is doing better than the alternatives. If you're taking some sort of risk in investing in something, then you should expect some greater reward. Now, if you can accurately predict what a stock is going to do, you can make some money, because obviously if everyone knew what the stock was going to do, then the stock would just be worth whatever the prediction said it would be worth. Everybody likes money, and there's a lot of data out there, but it's very hard to put it all together and then effectively use it. So here we have a graph of Intel Corporation in the red versus the S&P 500 index in the blue. Indexes are a popular way of looking at a stock and trying to decide whether or not it has performed well, because there are fluctuations in the market as a whole, and those fluctuations are not necessarily indicators that an individual stock has done well so much as the entire economy or sector. So if we look at the S&P 500 here, and then we look at Intel, clearly Intel has actually outperformed the market here by a sizable amount. So as of the time that I'm recording this, if you had invested in Intel last week, you would have made some money. So there are a lot of ways of looking at stocks and trying to determine what they're going to do. Indexing is a popular method. You don't look at individual stocks, you just say, well, the market as a whole is going to do well, and so I will just invest in things that represent the entire market. Value investing is a way of looking at stocks and trying to determine the value of the actual underlying company, and then trying to decide if the market has over or undervalued the stock. In cases where you think that the market has over or undervalued a stock, you might be able to make some money. Market voodoo is what I call looking at the patterns in the stock market going up and down and trying to determine some magical predictive mean where 3 humps indicates something, or there's a lot of very strange stuff out there, and it all seems pretty odd. I guess if enough people do it, then it'll be a self-fulfilling prophecy, but then you have to be the guy that sees 2.5 humps and goes. Because if you're not staying ahead of the curve, then you are going to lose money. So there's various methods of computer trading, which we will talk about in a moment. There's also buy what you know, which is just, if you like Coca-Cola and you think Coca-Cola is a great company, you go out and buy Coca-Cola. Or if you've got a friend who works at Motorola and you think, you hear all these great things about Motorola, then maybe you buy some Motorola. So for computer analysis, there are a couple of different methods that you can use. There are quantitative methods, such as neural networks, and static Bayesian networks. Neural networks are nice. They tend to be pretty complicated, and they're, in my experience, they're a little difficult to work with. Then static Bayesian networks, essentially you create a Bayesian network with a static design, you initialize the weights, and you use it. That might be good for immediate results and if you know a lot about what you're looking for in a stock, but your assumptions about what makes a good stock could be incorrect, and your network will not be adaptive to changes in the market. There are also qualitative methods, which qualitative should be in quotes here because obviously when you're using a computer, eventually it's going to be ones and zeros. But there are natural language understanding methods where you try to actually parse the meaning behind sentences. There are also statistical language models that attempt to correlate certain words and key phrases with certain activity, and those can be pretty powerful. So here we see an example of a Bayesian network. This Bayesian network has 4 nodes. The root node here represents x. Then there's a node representing y, z, and w. Each node contains a table of the number of instances that it sees in the input data that fit into a given location. So our root node x is essentially our we are trying to predict x in this case, and our root node has gone through all of the input data and generated its weights. Basically, if you have 500 things that are in column 1 and 200 things that are in column 2, it stores 500 over 700 in column 1 and 200 over 700 in column 2. And whatever those work out to, I should have picked better numbers. Those are your base probabilities for if you just picked some random thing in a data set. Now, all of the subsequent nodes say, okay, well, given a value for x or a categorization for x, how many things fit in column 1 for y, how many things fit in column 2 for y, and so on. So this is the conditional probability of y given x. And same here, this is the conditional probability of z given x. And this is the conditional probability of w given x and z. So each child inherits information from the parent and from all of the grandparents and so on. Once you get a new input, you can then go and look up the values in these various tables, and once you have the values for, suppose x is a Boolean, so it can be true or false. Those are your two categories. Then you look up all of the values assuming x is true and all of the values assuming x is false. You multiply all of the true values, you multiply all of the false values, and then you normalize those two results so that the sum equals 1, and you have your probability of it being true and the probability of it being false. Generating the probability tables, or the weights for each node, is very easy. You just go through and keep a table and look up which spot you need to put something in every time you get an input. Generating the graph itself is very difficult because you need to have some way of finding a way of linking all of these nodes together which makes sense. Our solution to this is a genetic algorithm. They are pretty simple and easy to implement and very effective, and you don't need to know anything about where you're going. It's an iterative process, it uses random variations, and it uses survival of the fittest to keep things moving forward. One issue is that you have to have some way of determining what fitness is. So the general flow of a genetic algorithm is that you create your population, you evaluate your population to determine which are good solutions and which are bad solutions, you eliminate the bad solutions, you make new copies of the good solutions to fill the empty slots that the bad solutions once occupied, and then you slightly modify those copies. If you've reached your goal, then you can leave the loop. Otherwise, you return to the evaluate step, and you look at which of your population is good and which of your population is bad. By going through this loop, you slowly, randomly generate things that are slightly better and slightly better and slightly better until you reach your goal. So now we will go through the program design. The program was written in Python. It's threaded, but it only runs in one process, so it can only use one processor at a time. It's approximately 800 lines of code, and then there are approximately 300 lines of code which produce the data. There are 5 main classes. The first class has a pretty weird name that was a mistake, but then it was kind of there and I never changed it. It is the main program. It initializes all of the data, it initializes all of the networks, and then it runs the genetic algorithm loop. There is a stock data object which opens an input file, reads it line by line, passes each line to a new stock datum object, and then stores all the stock datums for later use. A stock datum decodes a single line of the input file. It has 23 attributes shown here for fun. Where did the data come from? It was actually surprisingly hard to find the data. The stock quotes were pretty easy. Yahoo iCharts was very convenient for downloading those. In fact, you can generate a CSV file with whatever range of data you want. It took me quite a while to find data for all of the other information, I eventually found ycharts.com, which has it all in a uniform format. There's a BayesNet class, and the BayesNet class represents a single Bayesian network and provides all the interfaces that you need for scoring and mutating those. Then there's a Bayes node. A Bayes node is a single node in a Bayesian network. Now it's time for a program demo. So let's go to, here's my data procurement folder. You can see here there are a variety of programs here, and here I will just run this script and generate some yearly stock data. So now I've generated some stock data, and let's look at 2009. So here you can see for 2009, for all the various companies of the S&P 500, I have different entries from different dates with a current price, a future price, which is actually the price from the next date. It's actually going to be quite a bit after the financial statement comes out, but that's fine for our purposes. Then various items of data. Now if we go to run a program, here's a program that runs on a small data set. So here you can see it prints out some information, and then it starts, for each iteration of the genetic algorithm, it prints what the the previous best version did and what the new best version did. And here you can see it converged very quickly on the small data set that we've handed it. So now it's just running the rest of the 50 loops that I told it to. And now here's its attempt to generalize. Now, since this was such a small data set, it really was not particularly good at predicting anything. This right here is a sample tree. This is the tree that it produced. And so that's that. Now let's look at the results. So it converged pretty quickly on a small data set. That means that it learned the data very well. But that also means that it overtrained on the data. It's not a particularly good thing to fit the data perfectly. Really, you want to generalize. Here is predictions on a much larger data set. I believe this is all of the data from the S&P from 2011. Now you can see it never actually approaches 1. It actually tops off just over 80% accuracy. Again, this is the accuracy on the data that it's training on, not the accuracy of all data in general. Whether or not it's generalizing or overtraining has yet to be seen. Now here is a plot. Essentially this is, once it was trained on the 2011 data, the 2012 data was plugged in to see how good the predictions were. Now here is the a posteriori probability from the 2011 data. And here is the rate at which the stocks outperformed the S&P. So here you can see that there is actually a slight trend, and the more certain we were from 2011 that a stock would perform well, the more certain it actually performed in 2012. So this means that we are actually generalizing slightly, and that is exciting. So let's go through some conclusions. The program learned from the data. We showed that. The description that a network is capable of is limited by its size. You can only fit so much information in a network of a given size, and so when we limit the size, we limit how specific it can get. But that's probably a good thing because we're looking for generalization. We can see that some generalization occurs. We had loose predictability of future data. It wasn't perfect. If it was perfect, the slope of that line would have been 1. It would have been 1-to-1 correspondence. But having any correlation is pretty nice. So far it's only been run on small populations because the program is very slow. That tiny data set took all that time just now. For larger data sets and larger populations, it takes hours. So I would like to rewrite the code so that it runs much faster, and that way I can run it on larger populations, run more loops, and possibly run a certain number of networks and then average the results and see what that does. So that is the end of my presentation, and thank you very much for watching, and